Hello and welcome back to Calculus 3. This is the last section of chapter 15, Lagrange, multipliers. This is the procedure to find out minimum and a maximum of a function under a constraint. You can tell which classroom I teach in by these sprayer bottle, because these black lines are always drawn by me. Why? Because I want to have a three-dimensional object, which is this water bottle, and I would like to find its maximum. Where's the maximum? Well, it's clearly going to be on top of the bottle, right? But where is the minimum? Where is the maximum under constraint that it has to be on a black line? Well, it's right there, right? So that's the difference between previous lecture and today's lecture. Previous lecture, you have a shape that is given to you, and you are going to look for maximum on that shape, and that's going to be this point here, whatever XYZ equation you have for this bottle. The lecture today on Lagrange multiplier is the one that says find the maximum on the surface of this object, but it has to be on this black line. You have a constraint, and that's going to be this point right here. So that's the difference between the two. Now, how do we find it? Right? We're going to have a 2D version and a 3D version. They have the same equation. 2D version will have a two variable gradient, and the 3D version will have 3 variable gradient. So the equation that we want to solve to find the points at which min and max occur are going to be del f is equal to lambda del g. Now, f of xy, let's just say del of xy for 2D version, equal 0 is what we call objective function, and this is the one that you're maximizing or minimizing. And then g of xy equals 0 is a constraint. Now this could be xyz, could be xy, could be xyzw if you want to have a 4-dimensional or whatever. So this works in any dimension because, as you can see, your vector equation can have any number of dimensions in it. So let's work it out. Let's say problem 8. It says f of xy is given as xy squared, subject to the constraint x squared plus y squared equals to 1. What can this be? It can be, let's say, a temperature distribution on a disk, unit disk, right? Which has radius of 1 centimeter, 1 inch, 1 meter, whatever. And you are going to find the maximum and minimum temperature along the edges of that disk, for instance. So that's something that you can compute. Okay, great. So what is the procedure? Well, clearly we have to find del f and del g, so we start there. Those are vectors of partial derivatives. You're taking the partial derivative in respect to x, which would be y squared, and then a partial derivative in respect to y, which is going to be 2xy as a partial. The right derivative of y squared is 2y, and x is a constant, so 2xy partial derivative in respect to y. maybe I should, let me just here briefly say that as a reminder that the del f is fx comma fy, partial derivatives, and then del g would be gx gy as partial derivatives. So that's what we have. So now, anytime you start Lagrange, the first order of business is to find del f del g, and then we're going to stuff that in the equation and go from there. So del f del g, partial derivative in respect to x. Now, guys, this is going to be your g. Your g of xy is going to be x squared plus y squared minus 1 equals 0. So you make it into implicit form, and then you just take the derivative across the board. So partial derivative 2x, partial derivative 2y, and we are done. So now we summon our equation del f equals lambda del g, which is, when we plug this in, y squared 2xy as a vector equal to lambda times the vector 2x 2y. If you had linear algebra, or having linear algebra, you know how to solve these systems. You equal the first, right? They have to be the same. So you're writing the, let's say, orange equation, which is y squared equals to, do what?
We literally just did this.
2 lambda x. And then the blue equation is to equal the second ones. Now later on when we have a 3, right, you'll have the z one as well, so it'll be another color. 2xy equals 2 lambda y. And please observe that you guys have 2 equations here and 3 unknowns. So you will add the constraint into a mix as an extra equation to get enough equations for the number of variables you have. So we'll have x squared plus y squared equals 1 in the mix. So need g of xy to have enough equations. Again, 3 variables, 2 equations, no bueno. 3 variables, 3 equations. Excellent. So now I have my system. This is nonlinear system, and the only method that we have for solving these systems is called good luck. That's it. Whatever you can make it work, work. Now, in general, there are some good practice. That would be, if you can kill lambda, kill it, because lambda does not play a role in your calculations. Another piece of advice is do not cancel variables on left and right. Look at the second equation. You might be tempted to cancel those y's, right? If you cancel the y's on both sides, well, that immediately means that y cannot be 0. Now, is that okay in some cases? Sure. If I'm optimizing something that has length, let's say I want a volume for something, well, clearly you can't have one of the sides to be 0 because you would not have any object, right? You can't have this classroom and have either x or y or z to be 0 because the classroom would not exist as a 3-dimensional object, right? So in some cases, when you know what the application is, you can go ahead and cancel y's in the second equation, in the blue equation, because you know that dimension y, which is in that problem length, cannot be 0. But this is not a problem that is applied problem. Y could be 0. So I am not allowed to cancel a variable. Now, I can go to an equation, equation 1, and I can say that 2 lambda, now I'm just going to try stuff, okay? I'm just trying stuff. I don't know if it's going to work or not going to work. I'm just going to try. So on the first equation, 2 lambda is equal to y squared over x. Now this still says x can't be 0, but let's see what we get. We can test for y equals 0, x equals 0 separately. I just don't want to lose any solutions. If you need an example and further explanation, guys, remember that x cubed equals x. If you cancel this, you are losing a solution, right? Because if you cancel x's, you just get x squared equals 1. And that gives you plus minus 1, right? What happened with your 0? Well, because you canceled x's, you lost that solution. The proper way to solve this equation is to say x cubed minus x equals to 0. And then when you factor x, you get all 3 of your answers, right? So these are some tips and tricks that were there in algebra, right? And then it, same thing to solve trigonometric equations and so on. So losing a solution is not a fun, right, thing to do. And you usually lose a solution if you just cancel variables on left and right without prior knowledge that that variable absolutely cannot be 0. So be careful, do not cancel stuff unless you know it's okay to cancel. So why did I do this? Because I'm going to plug into equation 2. Now please notice that I didn't solve for lambda. I solved for 2 lambda because I also have 2 lambda and I'm going to replace that as a block. So now my blue equation is 2xy is equal to, and instead of 2 lambda, I write y squared over x times y. This is begging to cancel. It's begging. When I move x to the other side, I get 2x squared y is equal to y cubed. Well, y cubed minus 2x squared y equal to 0. Factor out y, and you get y squared minus 2x squared equal to 0. From where you get that, hello, y equals 0. Well, luckily we didn't cancel that one, right? And we also get the second equation, y squared equals 2x squared, which plug in equation 3. Now your equation 3 was x squared plus y squared equals to 1. So 3x squared equals to 1. X squared equals 1/3. X equals plus minus root 3 over 3. What are my points? Root 3 over 3 and 0. And negative root 3 over 3 and 0. No, those are wrong points. Those are wrong points because they don't work. I have to, sorry, hold on. Erase the points. I got I got this, and I got this. So now that I have these points, plug them in G to calculate the other coordinate. So these are 3 separate points, right? There is y, and there are 2 x's over here. So I need 2 y's, and I need an x for this one to calculate the points. So now we use G of xy to get missing coordinate. So it's x squared plus y squared equals to 1. If y is equal to 0, then x squared is equal to 1. X squared becomes plus minus 1. So we get 2 points, 1, 0, and negative 1, 0 from y equals 0. Then we use x squared plus y squared equals to 1. And then we can just say, for x equals plus minus root 3, when you square positive negative root 3, you always get 1/3. So it's going to be 1/3 plus y squared equals to 1 for both cases. That's y squared is equal to 1 minus 1/3, which is 2/3. And then I have to take the square root, so y is equal to plus minus square root of 2/3, so that's root 6 over 3, right? I'll just put 2/3 first, which is plus minus root 6 over 3. And observe that your x coordinate is plus minus, your y coordinate is plus minus. How many points does that create? 4 points. You have positive root 3 over 2, positive root 6 over 3. No, positive root 3 over 3, positive root 6 over 3, negative root 3 over 3, positive root 6 over 3, positive root 3 over 3, and negative root 6 over 3, and both negative. Negative root 3 over 3, and negative root 6 over 3.
So there's a total of 6 points there.
Yeah. Total of 6 points.
What is this representative of that we're finding?
Okay, well, glad you asked. Do any baking?
Yes.
Good. We're going to use this reference again. So, imagine a cookie dough. Cookie dough is not necessarily flat on top. It has some curvature to it, right? And it's large. You take a cookie stencil that is 1 inch in radius. So it's a 2-inch wide circular stencil. And you have your cookie dough, which has all of these ups and downs because it's not even. And you press that stencil into the cookie dough. And you get a cookie. Now that cookie is a disc. Now when you look at the edge of the cookie, you have all of these mountains, right? Those are the max values at these points. And the minimum values at the...
So it's everything...
You got to sort them out with the second derivative. I'm not doing that. But you got to sort them out in the second derivative to figure out which one is the min and which one is the max.
So in that metaphor, it's everything within the stencil. It's all those bumps within the stencil.
No. Only on the edge. Because your constraint, is x squared plus y squared. If you want to know the stuff inside, you're going to use previous section for min and max, right? This is going to be with the constraint, so you have to be on the edge. So here is another example. Take a CD, well, you don't know what CD is, the Blu-ray, right, disc. I'm joking. So you take a disc, I don't care whether it's a Blu-ray, DVD, or a CD, right? They all have the same thing. You pop them into your player, the laser heats it up, it's going to be warm, right? Is it really perfectly uniformly warm? No. At the edges of the disc, you will have somewhere higher temperature, somewhere lower temperature. There's going to be a lowest temperature on one of the sides, highest temperature somewhere, right? That's what you're detecting. Now, if you want the distribution in the middle, you're going to use the previous section because that one pokes out everywhere else.
My only question is so how do you know that g of x will be a constraint on f of x? So in the terms of like the cookie and dough and the cookie stencil, how do you know that the stencil, which in this case is g of x, isn't cutting sideways, where it's not even on the portion of
Well, first of all, right, you have your f of x, y, f of x, y, has x and y as the input, and then your g also has x and y as input. So they are overlapping on the same xy plane. Because if you're cutting it sideways, right, you stab it from the side, well, that's yz or xz. It's not going to be xy. So if you have xy for f and you have xy for g, then you know they are on top of each other, right? So that's at least giving you that sense. And then if you get g that it's not contained in f, then you're not going to get solutions when you start solving these, right? They're not going to work out because they will have no intersections.
But in the algebra, so like, for instance, for this equation here, for like what we just did there, we obviously have some function and then a sphere around it, because that was our x squared and y squared.
X squared, y squared is a circle, not a sphere. Sphere has to have the z squared as well.
So it would only pick up the points that are overlapping. The algebra rules out any other point, basically.
Which is, we don't care about any other point because we only care about the overlap because that's where f and g meet.
Yeah.
That's why you have a constraint.
Okay.
Right? If you don't care about the constraint, then you go to the previous section. So the thing that we, like, previous section had f of x, y, right? This section has f of x, y as well. But it has the g constraint in addition. So we care about the intersection. So does this problem, at least the procedure why made sense? Let's review it one more time. Where did I start? With some fxy and some constraint g. This is a lot of fun to actually figure out what these are from word problem. Like, this is just, given to you and then you just plow through it. So you find both gradients, you equal them through the Lagrange function equation, and then equal I components together, equal j components together, and add g into the mix to have enough equations. Solve any way you can. Eventually, it will spit out the points, and those points are the ones you are considering for your min and max. Through your wonderful second derivatives, right? You have your f of x, right? So go ahead, find your second xx, yy, xy, calculate d, right? And all of that stuff. So that entire portion is to be done for each one of these points to sort them out, which one is min, which one is max, and so on. So that you have, but we are only learning now Lagrange procedure. If you want to know what each one of these functions is, use the second derivative test, right? Use d and fxx. They can be saddle points, they can be, right? So. Great. That was fxy. How about fxyz? Yes.
One more quick question. So when you're like with the bottle you have there, the spray bottle.
Oh, this one is fxyz.
Okay, but
this is not 2D.
I understand that, but so if we have, would we get the same results of leaving our constraint being the ellipse that forms that black line, as well as intersecting a plane that cuts the exact same way?
Well, that's see, when I was explaining this for the first time, this looks like an ellipse because if I put it this way, it's actually a circle.
Okay.
So this constraint in the domain gives a circle of radius, let's say 1 or 2 or whatever. But then when that one cuts through the object and you look at the object, it looks this way. And it has a maximum.
Okay, my question is like more based on if I did the same math, like took the Lagrange multiplier, or however you phrase that, of having g of x being a plane cutting through that exact same way as you created that circle, as well as, and then I did a separate problem in where g of x was just the circle itself. Would I get the same?
You can't cut with the plane. See, that's the trick, because the g equation sits in the domain. It's not a plane, three-dimensional plane that you cut with. And what happens is your g of x is actually a shadow sitting on the bottom. That's why I said you take a stencil and you push into cookie dough and you get the circle. That circle is in the domain.
Okay.
Right? So what I had when I drew this line on this bottle was actually this way. So if you look at this way, it's actually a circle, right? The way I have it, it's a circle. But the way it looks on the surface of the bottle is not a circle. It's right. So it's in the domain. But now we are going to take a three-dimensional object and cut it with another three-dimensional object. So now our constraint is going to be three-dimensional, which is you have a shape, you are intersecting that shape with another shape, and then they are going to create some kind of edge outline.
Okay.
So at this point, you should imagine intersecting, let's say, how about make a ball, like a basketball, out of clay or silly putty or whatever the modeling thing for kids, right? And then stick a cone through that ball. You are going to have these intersections of circles where the cone, right, went into one end and went to the other end. You're going to have these intersecting lines. Let's find min and max on those, right, when you intersect the objects. So now we're going to have a f with xyz and g with xyz. It takes some visualization to grind. I mean, grinding through the problem is a procedure. Step 1, step 2, step 3. Right? If you're truly trying to understand the mechanics of this, then yeah, you have to turn off the light and let your brain render all of this in your head to truly understand what's happening behind this wall of calculations. So I really don't know which ones of these are nasty and which ones are easy by looking at them. So we'll just pick one and hope for the best. Because we're going to get 4 equations for unknown nonlinear system in any of these problems. So, so let's just, pick a lottery number, 24, and go. So f of x, y, z, your constraint, so subject 2, is going to be x squared plus y squared plus z squared. Yeah, you want this to be a ball, but minus xy equals 1. I'm going to ask you to try and get Lagrange equations by yourself. You know that you need del f. You know you need your del g. Multiply g by lambdas then for each one of the three components, n equal x to x, y to y, z to z. See if you can get to equations. Then we'll solve together. No pressure, you have 15 seconds.
What are you doing?
Comment on it. Comment on it.
I knew it was my picture.
Yeah, there is.
I'll support you. How's your calculation over there, done?
I love that.
All right, so let's see. So del f, partial derivative in respect to x, that's just y. Partial derivative in respect to y, well, that's x. Partial derivative in respect to z, -1. Del g, partial derivative in respect to x is 2x minus y. Partial derivative in respect to y is 2y minus x. Partial derivative in respect to z, 2z, and that's it. Now we have our equation for Lagrange del f equals to lambda del g, and we have y comma x comma -1 equals to lambda times 2x minus y. Oh, this is going to be awesome. 2y minus x and 2z. Wow, this is going to be great, guys.
Great lottery pick.
Yeah, this was a good, yeah. Look what's happening here. So I have my orange equation, which is the first. I have y equals lambda times 2x minus y. Then I have the blue one, which is the middle, which is x equals lambda 2y minus x. And then I have green equation, that says -1 is equal to lambda times, well, 2 lambda z. 2 lambda z. And then we have our g equation, which I kept purple, which was x squared plus y squared plus z squared minus xy equals to 1. So here is my system of 4 equations and 4 unknowns. something extremely important is happening in this problem. Please observe first two equations. When they are having this behavior, they're called symmetric, and the solution for the entire problem it becomes very, very simple. Ready? Equations are symmetric when you can swap x for y and get the same equation back. Do you see how the blue equation, if you swap x's and y's, you're getting orange? Or in orange, swap x for y, you are getting blue. If you have two equations with that behavior, they're symmetric equations, which means x equals y. All right? So if you see symmetric equations, that immediately means x equals y. Because symmetry. How do you know that equations are symmetric? You can swap x and y and you are getting the same equation. So if I swap x for y's, I get x, and swap x with y, I get y, which is this y, and so these two equations are interchangeable if you swap x for y. So if you have a pair that is, now if you have the triplet, that's even crazier, then x equals y equals z. Boom, done, right? But in this case, you have only a pair of them, and that immediately eliminated one of the variables. So now our four variable system is becoming a 3-variable system, and we do not care about lambdas, so it becomes a 2-variable system. So it's a huge time saver if you have symmetric equations. So we just discovered that y equals x from these two equations, and now we can simplify the system greatly. I don't care which one you're going to pick, orange or blue. You will replace either all x's or all y's with the x or y, and then you will calculate. So since x equals to y, I'm going to replace each x by y. So from equation 1, since x is equal to y, I'm going to write y equals lambda 2y minus y. And that gives me equation 1, new equation 1, y equals lambda y. What did I just found? Lambda is 1. I don't care about lambda, but I just found lambda is 1, just came up. So immediately I go into green equation. Lambda is 1, I know z. Right? So that's how awesome this thing is. So lambda is equal to 1. You don't have to calculate lambda, but when it's convenient, hey, if it's free, let's go. So now we have lambda is 1, so negative 1 is equal to 2 times 1 times z. So z is equal to negative 1/2. Great. Now from equation 3, I know x is equal to y. So I have x squared plus another x squared plus negative 1/2 for z squared minus x squared equals to 1. One of the x squares dies due to negative x squared. And negative 1/2 becomes a quarter. So I have that x squared is equal to 3/4. X equals y equals plus minus root 3 over 2. Now you might be tempted, you have to be careful about this, guys. You might be tempted to write 4 points for positive root 3 right, over 2 and negative root 3 over 2. But you can't write 4 points because x must be equal to y. So when they have opposite signs, it's not going to be the part of this problem. So let me just, so we have now these points. I have these, and I have the z value. I use the z in G to calculate these x and y's. So when I look at these, well, I don't want to box these because that's not the answer. What are the answers? The answer is a root 3 over 2 and another root 3 over 2 and negative 1/2 as a point. And negative root 3 over 2 and another negative root 3 over 2 and a negative 1/2 as a point. I do not get 4 points because I cannot have negative root 3 and positive root 3 because condition of the problem was because of the symmetry that x equals y. So I don't get to pick the cross ones like I had in a previous problem. Previous problem did not have this condition, therefore we were able to have positive with negative. Now positive with positive and negative with negative only. Problems are good for, killing time, carpal tunnel, a lot of things. Since like 2-3 years, you find yourself with nothing to do. I can crank some Lagrange.
Hope I'm not doing that. That's great.
Why? It's fun. How about we take a look at shipping regulations, box with minimum surface area, maximum area of rectangle in an ellipse, maximum perimeter of rectangle in an ellipse, minimum distance to a plane, minimum distance to a surface. See, all of these things, because you guys constantly keep calculating these things when you do work, right? You are a mechanical engineer, right? You have to figure out these kind of things. The shipping regulations and all, that's packaging engineering. It's awesome, right? You want to find the maximum volume and you want to minimize the surface area because the less surface area your box has, the less material is used to make that box. If you shave 10 cents on a material on one box times 100,000 boxes, that's a savings for a company of $10,000, right? So you have to understand that companies and corporations, right, they are not stingy for 10 cents, but they are stingy for 10 cents times 100,000 units, which is $10,000, right? So of course we're going to be stingy on that one. So optimizing is very important, and this is a form of optimization. So let's do you want shipping regulations or you want box with minimum surface area? Let's do shipping. All right, fine. Shipping. So now you're working for UPS or FedEx or something. Oh, no one says postal services. We should go directly to postal services, but we don't. Next time someone mentions socialism, say postal services. It's government operated. Obviously, it's falling apart like everything else that's government operated. Anyway, shipping regulations 27. A shipping company requires that the sum of the length plus the girth of the rectangular box do not exceed 108 centimeters. So we have a box that is going to be shipped into the world. The length of the box is here, so I'll denote that with a red line, and the girth is going to be this. The face over there. So I have my x, and I have my y, and then I have my other y, and my other x and L. So they say the shipping company requires that the sum of the length and the girth of rectangular box do not exceed 108 inches. So technically the equation that I can write is 2x plus 2y plus L is, well, do not exceed 108. So the worst you can have, like the most you can have, is 108. That's it. Find the dimensions of the box. So what is x by y by L? That's the dimensions of the box. With the max volume. Obviously you want the maximum volume. Maximum volume means the most space in the box. So you can put a lot of stuff. So you're looking for maximum volume, but you have the constraint of that equation up there. Now, volume formula for a box is hopefully XYL. That should be a equation. So what's my f? My function f of XYL is XYL. And my g of XYL is 2x plus 2y plus L minus 108 is equal to 0. So we are able to take the word problem and transform that word problem into this. And now we just solve it. We have our del f equal lambda del g. So partial derivative of f in respect to x is yl, partial derivative of y is xl, and partial derivative in L is xy, equals to lambda. On the other side, partial derivatives are, we have in respect to x, 2, in respect to y, 2, in respect to L, 1. Create 3 equations and use g as the fourth. So yl equals 2 lambda, xl equals 2 lambda, and xy equals lambda, and finally the g equation, which is 2x plus 2y plus L equals to 108. What do we know from the first 2 equations? What do we know? What can we swap and get the same equation? X and y. So first 2 equations are symmetric. I mean, guys, you can also solve this by saying YL equals XL. Now, L cannot be 0 because then your box would have no depth, right, to put anything in it. So you can then cancel these L's and you have X equals Y, right? Or you can just make the argument, well, they're symmetric, so immediately X equals Y. Now, if X equals Y and you plug that in here, you get X squared equals lambda. So there you go. So x squared equals to lambda. Let's say xl equals to 2 lambda. So when you plug in there, you get that xl equals 2x squared, we know that x cannot be 0, it's length, so we can cancel in this case. L equals 2x. Great. I have x equals y and L equals 2x. So now I can plug everything in my equation here, since, let's go orange, I guess. I have 2x plus another 2x because x equals y, plus instead of L I write 2x as well, equals 108. This all together is 6x equals 108, and x is equal to, is that 18? 6 times 8, 48, 60, yep, 18. Now L is equal to 2x, which is 36. So dimensions are 18 by 18 by 36. I believe these were inches for the box. There is no prescribed way to solve the nonlinear system. You just keep pounding on it until you get it. The greatest tool to have, greatest help, is to realize and recognize when you have symmetric equations, so you can make x equals y, or x equals z, or z equals y, or x equals y equals z if it's three-way symmetry. You can spot the symmetry. Like, look at that problem 26. This problem is really symmetric. This is going to have, like, you see the problem 26. We're not going to do it. You can do it as practice. But if you see problem 26, it says fxyz is equal to, and you have xyz to the 1/2. That's like a square root of xyz. So let me write it as a square root of xyz. And the constraint is x plus y plus z equals 1. This is a three-way symmetry. It doesn't matter what you change with what. Doesn't matter in which way you put x, y, and z, you cannot change these equations at all. Just by looking at this problem without solving anything, immediately I know that x equals y equals z for this problem. Because these equations are so symmetric that it doesn't matter which way you rearrange these, you will always have the same equation. So when you take derivatives, it stays the same. You take, right, you put all these things. So this problem is guaranteed to be x equals y equals z. Guaranteed. So, do it. Symmetry is going to give you x equals y equals z. Now, is this a solution? No, it's not a solution. This is just an observation that's going to help you solve the equations, because you are going to get it. Don't forget your partial derivative with the square root, right? That's going to be xy over the square root of xyz. So, right? So, solving the problem is going to look awful, but as soon as you get those four equations and you go to those partial derivatives and gradients, when you get to the point where you get and you recognize the three-way symmetry, x equals y equals z, all of that collapses to two equations. You kill your lambda immediately and you're done. So there's that. So as I mentioned, the project which I uploaded a week ago or 10 days ago or something does have a Lagrange problem. It's the one with the watches. So you will create two equations, the constraint and objective equation, and you will just crank Lagrange and solve the problem. There will be one problem on the exam and definitely one problem on the final as Lagrange. If you request for more problems, obviously on the integration test, let's say, I can accommodate. It's It's a really good section.
Can we ask for
So that's
more
the one.
questions?